So our problem today is a capacitor with a 3 millimeter gap has a potential difference of 6 volts. A disc of glass 1 millimeter thick with the area the same as the metal plates has a dielectric constant of 2.5. It is inserted in the middle of the gap between the metal plates. Now, what is the potential difference of the two metal plates? First, let's draw the capacitor without the glass and write down what we know. The potential difference without the glass, which we shall refer to as the initial potential difference, is 6 volts, and the change in position is 3 millimeters. Next, let's draw the capacitor with the glass. It has a width of 1 millimeter, so the space between the capacitor not taken up by the glass must be 2 millimeters. The dielectric constant of the glass, symbolized by the letter K, is equal to 2.5. Now we can start thinking about how to solve this. What has changed? We've introduced an insulator into our system. Does that change the electric field? Yes, the space taken up by the glass slab changes the electric field. How? Well, first we'll have to find the initial electric field. In a capacitor, the electric field points in the direction of the negative plate. Knowing that, we can use the initial potential difference and the potential equation to solve our problem. The potential equation is the negative electric field dotted into the difference of position. Since it's only moving in the negative x-hat direction, we can simplify this equation to only include the x values of both terms. Then, if we divide by the x term of the change in position, then we get the negative potential difference over the x term of the change in position equals the x term of the electric field. Plugging in our values, the x term of the electric field, which is our E initial value, 2000 volts per meter. Now, all we need to do to know how the electric field has changed is to find the electric field in the insulator, which is equivalent to the initial E field divided by the dielectric constant. Plugging in our values, we should get 800 volts per meter. Now that we know what the entire electric field looks like in the capacitor, we can finally find the new potential difference. It is equivalent to the electric field of each third multiplied by the width of each third, but the first third and the last third have the same electric field, so you can just write it down as shown, and you should get 4.8 volts.